I'm supposed to summarize the collaboration work on fast radio burst and related sciences. And since there is so much been going on in the last couple of years, I won't be able to cover everything, of course. So I'll just give some highlights for very recent work that got the attention of many in the collaboration, across the collaboration. So this should work. So I intend to shortly give some overview of the observations, a very brief overview of observations, so just that people can get a feeling of the diversity of the phenomena and the challenges. But let me start with some introductory remarks. So in case someone haven't been around, fast radio bursts are these extragalactic radio flashes of millisecond duration that come from all directions. And you can actually see an example here. This is, in fact, the very first burst reported in the literature. And that was in 2007. Since then, over thousands have been detected. And the detection rate keep increasing thanks to commissioning of new telescope, etc. The origin is largely unknown, with some exceptions that I'll mention shortly. And I think that what makes them very attractive to the astroplasma community and the laser plasma community is the fact that they can serve as natural laboratories for extreme plasma physics. So the discovery of FRBs, in fact, sorry, I got something in my voice, open new frontiers in extreme physics. So first, they probe regime far beyond reach of terrestrial experiments, and I'll show an example shortly. They motivated investigations of coherent emission at enormous luminosities, which is extremely challenging. And they exhibit a wide range of light curves, spectra, polarization properties, etc., which might be indicating multiple progenitor channels, different emission states, complex environments, strong propagation effects, probably all of those. And I personally think that it's really should be one of the efforts to try and entangle these different effects. And this is one of the goals, actually, of the collaboration. And finally, they recently have been used as new probes of cosmology. This is beyond the scope of this talk, but I'll just show one slide. So, as I mentioned, there has been a substantial progress in the last 2.5 years in by SCICS. And I listed 3 main categories related to FRB science. So first, there has been a quite intensive study of different emission mechanisms from first principles, also using new tools developed in SCICS, like Entity, and I'll show some simulations. Also, many studies by Manuela, Lorenzo, and others on propagation and escape of these pulses, which is one of the core issues. And finally, we already heard about magnetar eruptions and transmission of waves to the magnetosphere, which is maybe the main process producing these waves. So as you can see, this work involves quite a large number of people across the collaboration from several institutions that are listed here. So this is indeed one of the main efforts. So let me very quickly say a few words about observations. So first, from all sky maps like this one, observers infer that the distribution on the sky is isotropic. And this is not surprising. This is what expected from a cosmological population. The inferred rate is pretty large. It's maybe close to 10,000 per sky per day. And this is, I emphasize, this is the rate of bursts, not necessarily sources, because many are repeating. There is a large number of localization, over 90, I think. And this is very important, because this gives us a way to measure the distance of the redshift precisely. And maybe also to calibrate dispersion measures for purpose of doing cosmology with those. And finally, as far as I understand, there are over 60 confirmed repeaters now. A repeater, by the way, is a radio source exhibiting more than 2 bursts from same location on the sky. So there are a few dozen of those, but it could be that there are many more. We just didn't get to see repetition, maybe all of them. This is unclear. And I think, yeah. The luminosities of FRBs are enormous. They're somewhere in this range. And there are also some which are even much brighter. And to me, this is really amazing, because given the low efficiency expected in essentially all models, below 10 to minus 3 or so, it means that the power of the explosion is huge, is larger than giant flares. There is no problem with the energetics, but the luminosity. So clearly there should be some sort of, at least for the bright burst, should be some sort of beaming, flickering, I don't know, such effects. They're also much brighter than any other known pulsar bursts. You can see it here. This cluster delineates the FRBs. These other sources are non-pulsar bursts. And as you can see, it seems like 2 distinct populations. These luminosities are larger by orders of magnitude. So this could probably point out to a very different emission mechanism. Okay. Also, the brightness temperature, as you can see in this diagram, is enormous for all of these sources. So it's somewhere in this range. And, well, like tsunami, I guess Roger would say. And I think this indicates, I mean, combine these two, it indicates that whatever produced these bursts must produce coherent emission at huge isotropic equivalent luminosities. And this is a real challenge for many of the models. Here you see some examples of burst morphologies taken from the first CHIME catalog. Just to get a feeling of the diversity of the phenomena. So you see some have broadband spectra, some narrow, some show this downward drifting, so-called set trombone effect. So it's kind of interesting. The thing I want to emphasize is that quite a large fraction of the bursts show these very narrow spectral bands. And this is really challenging to theory. And I'm going to show that it can actually be produced by strong cooling in coherent emission sources. So that might be one way to do it. All right. Polarization. So again, there is a wide range of properties, but I think many shows this very high degree of linear polarization, sometimes approaching 100%. So you see an example here is this burst. This one has linear polarization, I think in excess of 95%. At the same time, others show circular polarization. There are also a few handfuls showing polarization angle swings and jumps. So here is, again, an example for such polarization angle swing. This may be a probe of geometrical effects, or who knows. And finally, they exhibit wide range of Faraday rotation measures with some very extreme values in some cases, which indicate extreme magnetoionic environments. There are a few, I think 3 or maybe 4 now, I don't know, that show also this persistent radio emission in addition to the bursting activity. And the origin of this persistent emission is really unknown. I think that tendency in the literature is to favor a magnetar with nebula origin. And if this is true, I think it indicates some, well, indirectly association with magnetar. There is one source, however, and only one so far, detected in our own galaxy from a direction of a non-magnetar. And it also exhibited coincident X-ray emission. So you see here the two radio pulses detected for this object. And here you see the two X-ray spikes detected in coincidence with the radio emission. And this is a direct indication that magnetar flares can produce FRBs. I think that it's unclear at present how rare they are among magnetar flares. This is something that I think is desirable to actually try and estimate it observationally. What's the fraction of magnetar flare producing FRBs? But I mean, it's an indication that they can do it. And finally, as I mentioned, they use cosmology probes. This is, again, beyond the scope of this talk, but I'll just mention, I think Vicky told me that they already resolved the so-called missing baryon problems by showing that these baryons, so-called missing baryons, reside in the IgM. And they have many more uses in this respect. All right, so what could be the origin of these bursts is unknown, but there is no lack of imagination among theorists. So there are quite a number of models proposed, and this is a partial list only. And I just want to comment that SCIC's researchers were involved in studying some of these other origins. The one I'm going to focus on, and the one I think that maybe it's fair to say attracted most of the attention of the community in general, is the so-called magnetar-based models. It could very well be that there is more than one class. There may be several distinct classes of FRBs. Who knows? Something like, what discovered for GRBs 30-something years ago. I'm still old enough to remember this. So that's a possibility. And maybe the diversity actually points to this. OK, before I'll move on to discuss FRBs for magnetars, I want to say a few general things about propagation. So propagation of ultra-strong electromagnetic pulses, EMPs, is one of the core issues in this business. And it's really not well explored yet. This is one of the current and near future efforts. Anyway, the response of the plasma to these pulses is characterized by one important dimensionless parameter. It's known as the strength parameter. And it's essentially the ratio of the wave electric field amplitude to the wave frequency in some units. It's given explicitly here. And this parameter quantifies how relativistic and nonlinear the plasma response to the wave is. To be more specific, it actually gives the maximum momentum an electron can accelerate to inside the wave. But I don't want to get too technical. So the regime A, much smaller than unity, is a regime where the wave is non-relativistic and linear. And this is well understood. Some might say even boring. The other regime where A is much larger than unity is the regime where the system is is highly relativistic and highly nonlinear. And the main question is, what will be the fate of the pulse in this regime? Is it going to survive or going to be damped? Now, you can express this A naught in terms of a luminosity, which is observable, and the distance to the source. And what you get for FRBs is these numbers. So A can be around between 10 to the 4, even to 10 to the 5th for typical FRBs if the wave is produced in the inner magnetosphere, or let's say in the vicinity of the light cylinder. So for these models, we are actually probing this regime where A is huge. And just to compare with the laser plasma experiments, so typically in laser plasma experiments, pulses can be produced with A in the range 1 to 10. But maybe in very strong lasers, they can approach 100. And compared with these 10 to the fifth, 4/5, we see that they indeed probe a regime unreachable in experiments. OK. So as I said, one of the core questions is what's going to happen. And the expectation is that there should be very strong absorption and scattering of these waves in the regime where A is large. Let me just point out that in magnetar environments, we are in a regime where the plasma is strongly magnetized, meaning that the Larmor frequency associated with the background field is much larger than the plasma frequency. The regime where the pulse propagated in unmagnetized plasma has been studied years ago, maybe not with peak simulation, but at least analytically. And there it seems that there is not much feedback, but in this regime, there should be feedback. And Emanuele Sabacci and collaborators in this very nice paper identified 3 distinct regimes, which are characterized by the wave frequency and the Larmor frequency. So when the wave frequency is smaller than this ratio, we are in the non-relativistic linear regime. Again, this is well understood. When the wave frequency is much larger than the product of A naught and omega L, the wave is relativistic, but its behavior, at least as shown by Emanuele for a 2-fluid model, is very similar to the case of an unmagnetized plasma. And there's not so much feedback expected. But in this intermediate regime, that's where feedback is expected. And there have been several studies by Yuri Lubarsky, Andrei Beloborodov, and others. But most of these studies explored actually test particle acceleration in a vacuum wave. In my opinion, this is insufficient to make strong statement, because first, the wave is not a vacuum wave. It has very different dispersion relation, and it's nonlinear. And it's unclear how this is going to affect this process, because this acceleration occurs in very narrow resonances. Second one is that it's unclear what will happen when feedback will kick in. So I think the way to study this, and there are now attempts in the collaboration, is using peak simulations for pulses with A is larger than you can do numerically. I think Navin Sridhar is working on this, and also my postdoc, with much help from Haik Akobian, are looking at this, and we'll see what comes out. So let me now move to discuss emission models, etc., for magnetars. So as we've heard already, it all starts with some sort of explosion, a magnetar eruption. And these eruptions are triggered maybe by a crustal quakes, as Chris told us, or some sort of sudden release of magnetic stresses, depending on the model. But in the context of my talk, whatever the mechanism is, the important point is that these eruptions, they shake the magnetosphere near the stellar surface, and this shaking produces disturbances or waves that propagate in the magnetosphere outwards. So depending on the type of waves and the specific mechanism, this wave will dissipate the energy at some radius. And most of this dissipation energy is expected to be released as high energy emission, X-ray and gamma ray flares maybe. But a small, though important fraction can be tapped to produce the FRBs, and I think the galactic magnetar is one demonstration of this. So here you see an example of X-ray flares for magnetar, and Chris showed some other examples produced by these eruptions. And here you see again the simulation by Kushik, this 2-dimensional image simulation by Kushik. And what I just want to emphasize here is that what they find, as far as I understand, is that these eruptions produce waves, both fast magnetosonic wave that you can see on the right side and alpha waves here, that indeed propagate in the magnetosphere. This is the inner region, and this is like a stretch out of the. So we now see from first principle that these eruptions indeed produce these waves. Now, what the fate is of this wave is, as I said, depend on the imagination of the theorist mainly. And there are quite a number of models proposed in the literature. And I listed some of them here. This is a partial list. I didn't have enough space to all of them. But they are commonly divided into two distinct classes. They're actually not distinct, but two classes. One called magnetospheric models. In these models, the disturbance actually steepens in the inner magnetosphere and produces the burst there. And for this class of models, the wave propagates in this regime of UJ. And the model I'm going to discuss in the next slide, the master shock model, belongs to this class. And the other type of model is a so-called faraway model. In these models, the disturbance actually reaches distances much larger than the light cylinder. And this magnetic ejecta then either collide with some intervening matter, producing a shock and emission by some mechanism, or produce the coherent emission by a reconnection event. I actually included here models like this, which are not really far away models. They're, I don't know, maybe intermediate. They're beyond light cylinder, but not that far. All right. So these models may actually avoid some of the challenges. Now, there has been a debate in the community, a lively and heated debate, whether FRBs can be produced in the inner magnetosphere or not. And I think there are arguments in favor and against. And as far as I understand, the main arguments in favor are observational, and in particular, one compelling one seems to be this report on detection of a scintillation signal in one of the objects, which actually limit the size of the source to be something on the order of 10 to the 9 centimeter, namely roughly the size of a light cylinder. And according to these papers, Pawan can correct me later, it's actually irrespective of the Lorentz factor. So beaming, I mean, this constraint includes beaming effects. There are other phenomena I described earlier, which also being used as argument in favor. I'm not sure how substantiated it is. On the other hand, theory introduced challenges, mainly claiming that these waves cannot escape from the inner magnetosphere. So one reason could be that in this regime of large A, the wave will be absorbed. And I discussed this already, I won't repeat it. But there are other processes, mainly parametric instabilities, that can dump the wave in the inner magnetosphere. So one example is here. In this process, the fast wave that should appear as the FRB if it escapes can split actually into two alpha waves or alpha wave and a fast wave. And essentially, if there is a background of alpha wave with large enough phase space, then this will suck the energy of the pump wave to the background. And since this process is exponential, it doesn't really matter what the background is. However, one point that I want to make is that this analysis apply in the low frequency regime, namely the regime where the wave frequency is smaller than the plasma frequency, which is below, let's say, 100 stellar radii or so. Mechanism that can produce burst at a radii where it's kinetic, namely its frequency is maybe in excess of the plasma frequency, that may not be susceptible to this process. It's not entirely clear what happens when the frequency is comparable to the plasma frequency. I think this is something which should be studied further. Okay, so let me move on now to talk about master shock. So Chris already mentioned this, and this got much attention in our collaboration. So this is a new type of shocks, I would say, discovered recently. I think it was first identified in simulation by Alex Chen, and then studied analytically, systematically in a paper, which in my opinion is a beautiful paper by Andre, although requires some efforts to read. No, it's really a masterpiece. And it's also discussed in our paper in the appendix. So anyway, the magic about these shocks is that they steepen at a radius of about 100 stellar radii or a few hundred stellar radii weakly, depending on luminosity, regardless of the magnetization of the background. So it doesn't matter what's the magnetization, the shock will form. When they steepen, sorry, I forgot to mention that what actually steepen is a fast magnetosonic wave, a compressive wave, compressive MHD waves. Again, when they steepen, they release most of the energy as high energy emission. This is still under study, I think, by the CETA group. But what we have found recently is that a fraction of about 10 to the minus 3 is tapped to produce a precursor wave emission, coherent emission, that for multiplicities quoted in literature comes out in the gigahertz range. So we propose that this might be actually might explain some FRBs. Let me just in a few words explain why they form. So the key point here is that the wave amplitude declines slower with radius than the background magnetic field. So for example, for a dipole magnetosphere, the background field drops roughly like 1 over r cubed, and the wave frequency drops like 1 over r because this is a quasi-spherical wave, so by energy conservation. And you see that the ratio of the wave amplitude to the background field increases as r squared. So even if the wave is produced as a linear disturbance near the surface, which is the case for most explosion, it becomes progressively nonlinear as it propagates outwards. At some point, this invariant approaches 0, and at this point, the wave steepens and forms a shock. Actually, the bottom part slows down abruptly and is being captured by the upper part. And the reason is that the plasma inside the wave actually diverges. I mean, the Lorentz factor of the plasma diverges. So, as I said, you can study analytically the propagation of the driving wave and the formation of the shock using characteristics, as Chris mentioned. But if you actually want to probe the kinetic structure of the shock and the emission, you have to resort to simulations, kinetic simulations. And they are hindered by the large-scale separation between the MHD regime and the kinetic regime. So the progress is that in the collaboration, we managed to do 1D simulation and very recently also 2D simulation of this process. And I'm going to show an example. So I'm going to show now a 1D simulation of a master shock. I'm going to start with the large-scale view. So you'll see the driving wave propagating in steepens. And here we have 10,000 skin depths per 1 wavelength and 10 wavelengths in the box. So this is really large enough to actually probe everything. And the upper panel shows the field. So this is the electric field, wave electric field in blue, and this is the total magnetic field, the sum of the wave plus the background. And the lower panel shows the velocity of the plasma in the wave direction. So I'm going to run the movie, and you're going to see what's happening. The wave is injected from this boundary and propagated to the right. You can see the plasma oscillating in the wave nicely as it's expected, and we expect shock to form when these two lines will touch. At this point, the invariant is 0. And if you look carefully, you see that the plasma will accelerate abruptly in a second when they will be very close. It actually accelerates towards the injection source. And come on, now it accelerates, and you see the shock forms, you see the dissipation, and another shock is going to form here in a minute. And clearly, this kinetic structure is unresolved. But you can, if you have good eyes, you can see this high-frequency precursor wave launch from the shock and propagate against the incoming plasma. And so to get some more insight into what's going on, I'm going to zoom in. So this is a zoom in into the shock region by a factor of about 1,000. So now you see the system on kinetic scales. And this is a snapshot. I'm going to run the movie, but this is a snapshot from early time after shock birth. So the shock is still very weak. It's subcritical, but you can see very nice train of solitons here in the upstream and the corresponding nasty peaks. And now when I I'll run the movie. You see that the solitons are dispersed, but there are two remaining here. And this to produce the precursor wave emission that you can see here. Right. OK, so by the way, I just want to comment that I don't have time to actually discuss, but that we managed to find an analytic solution that reproduced the structure, not the precursor emission, but this solitary structure quite remarkably. And what we learned from this is that the dissipation mechanism here is very interesting. It's different than collisional shocks or any other type of shocks, and it essentially involves a transition to chaos. So this system is, even if you write the model we constructed is time independent. So even for a time independent model, the equations are chaotic. And basically, this dissipation occurs by divergence of the trajectories. So this is actually an example of a non-linear system. OK. So to gain some insight into the emission mechanism, I'm showing a snapshot from the previous movie at late time where the shock is strong. So this is, again, the electric and magnetic fields. And I'm showing here in the middle panel the plasma velocity along the shock normal, as well as in the bottom panel, the momentum distribution. So you can see that the plasma here propagates in the first soliton crossing here. The plasma is extremely coherent. And you can actually see this ring distribution in momentum space computed in this interval here. And then in the second crossing, you see some divergence, which that's what I mentioned. But the plasma is still semi-coherent. You can still see evidence for ring distribution. And then you have a complete phase mixing and dissipation. So this ring distribution has been known for a very long time to be susceptible to the so-called synchrotron maser instability. So clearly, synchrotron maser is what we see here maybe. But we think that this is not the entire story, because when we look at the spectrum, and this spectrum was computed for some section in the downstream here for this wave, what we see is these harmonic peaks. And by the way, let me comment that this structure, very similar structure, have been seen before in planar shock simulation by Lorenzo and collaborators. Very similar. So anyway, these harmonic peaks turned out to be are associated with the distance between the solitons. So these are harmonic of this distance. And this distance, we find from the analytic calculation, is on the order of a skin depth, whereas the width of the soliton is about gyro radius. So for large magnetization, they can be very different. So what we think is that there is actually some additional physics involved, which we do not fully understand, to be honest. And this is something we are trying to understand better now. And again, from this detailed simulation, we find that the efficiency of the precursor wave production, namely the total dissipation energy tapped to produce the precursor wave is 10 to the minus 3. OK. Now, as I mentioned, very recently, there have been attempts to perform global 2D simulation. Of course, the advantage of the 1D simulation is that you can have very large resolution, and you can run them for long times. But of course, they don't probe the global geometry. So here I'm showing a simulation performed by Dominique Bernardi, a student in Yadji's group, of the same process. But now you'll see a fast wave injected from the boundary and propagated in a dipole magnetosphere. Yeah, you can see the fast wave injected here. And if you look at the bulk Lorentz fox, for example, you see the shock is formed now. And you can see that the arrows mark the streamline. So you can see that the flow pattern is quite involved, more than in the 1D case. But nonetheless, if you look at the equatorial plane, slice through the equatorial plane, even though the structure is not well resolved, you can see evidence for these two solitons and the precursor wave. So this seems to be in good agreement with the 1D peak, which is, I think, encouraging. Also, you can see the global structure. So there is a finite angular width for the shock, which can agree with some analytic estimates. All right. Chris mentioned this. There are also 2D simulation in a paper that was just posted on the archive, I think, last night or 2 days ago. And here, of course, MHD simulation cannot probe the kinetic structure, obviously. But they have other advantages I'll mention in a minute. Here you see, again, the propagation of a wave in a smooth dipole magnetosphere. And you see, as you'll see in a minute, you see formation of two shocks, actually. If you look at the equatorial plane, it looks very different, very similar to the 1D simulations. So you can see the shock. And I think the comparison between the MHD and the 2D peak yields quite good agreement. And I think this is important. So the advantage of this simulation is that you can actually study propagation of this wave in a more complex field. And you can see an example here where the field is perturbed, the magnetosphere is perturbed by launching this alpha wave along the closed field lines, and then launching the fast wave into this. And what's interesting is that you see that the shock wave is fragmented, so it breaks. So actually, the structure of the shock wave is kind of more involved than what you expect from the 1D simulation, et cetera. To me, this is very interesting because, and the expectation that in a more realistic magnetar magnetosphere, we will have these more involved structures. And to me, what's interesting is the question, what should be the observational signatures of this? Okay, so this is something that I think is desirable to study. Of course, again, you can probably not do it with PIC, but you can think of ways to somehow calculate the observed emission signal. Okay. So now I want to move to discuss cooling. So all of the simulation I just showed you ignored cooling. So there was no radiation reaction in the simulation. But we naively expect a radiation reaction to actually be quite important. So with Arno, we decided to try and generalize the models, both the analytic models that I didn't have time to discuss, that you see here, and PIC simulation, to include the full Landau-Lifshitz radiation reaction force, and then to run. And then we find some very interesting results, so I'll describe them. So first, from the analytic solution, as you can see, what we see is that strong enough cooling suppresses the amplitude of the solitons on the one hand, but increases coherency because of the cooling. And these two effects are actually counteracting the effect for the emission of the precursor wave. And it means that the scaling of the precursor wave is, with cooling is non-trivial. That's why we also needed the PIC simulation. The other thing that we find interesting is the dynamics of the wave. And here I'm showing the large-scale view, as I showed before, of the driving wave. And what we find that unlike the case where cooling is not important, where the plasma is accelerating all the way to the shock upstream, and in which case it's actually possible analytically to scale it to realistic magnetars, here the plasma accelerates initially, but when it meets the precursor wave, it starts decelerating. So there is a deceleration. And this means that the conditions just upstream of the shock are self-regulated by cooling. It also means that it actually decreases the ratio of the plasma frequency of the background field and the plasma frequency just upstream of the shock, which, as you see, is important. OK. The other thing we find, so here you see a suite of peak simulations for different degrees of cooling, starting with no cooling here, ending with ultra-strong cooling there. And what we find is that even if cooling is strong, it doesn't completely suppress the precursor. In fact, the intensity of the wave is somewhat smaller, but it doesn't scale with the cooling strength over 5 orders of magnitudes. But when the cooling is enormous, then it actually quenches. It quenches this entire solitary structure and quenches the precursor wave emission. So that's what you see here. And the other thing that you see is that when cooling is strong, but the precursor wave is still intense, the compression of the plasma increases the frequency of the wave. So if you look at the spectra here, the frequency of the wave here, for example, is larger by a factor of about 20. And this means that my simple estimates suggest that these waves, actually it's even true for marginally cool waves, are emitted in the kinetic regime, actually. So they can avoid the parametric instabilities I mentioned, I think. This is something we still need to explore a bit further. And finally, as you can see, strong cooling leads to these extremely sharp peaks, even here and there. And so I think this might be a general conclusion that coherent emission in the presence of very strong cooling can actually produce these sharp peaks. And in relation to the very narrow spectral band observed in many of these bursts. So I don't know, that might be one way to do it. All right. OK, so I have to finish soon, but I just want to say a few words about alternative mechanism. So quite a number of alternative mechanisms have been studied by SCICs over the last, 3-4 years. And I would say that there are 2 types of these models. One class of models are models where the coherent emission is produced by a reconnection event. So you can see it here, a collapsed current sheet that shakes the magnetic field line and produces these fast waves. The efficiency is not large. It's on the order of 10 to the minus 3 or 4. So it's comparable to other models. So this is one class of models. And there are here an example of 2 scenarios where it's be relevant. One scenario in which the fast magnetosonic wave compresses the stripe wind of the magnetars, produces this reconnection event. Another possibility is this plasma ejection by Alphen waves, as discussed in the paper by Yaji. So this is one possibility. Other possibilities are emission from a shock. So I didn't mention the older models where shock are produced far away and produce massive emission. This is similar to what I discussed on master shock. But there is one idea, interesting idea by Chris, a recent idea where these shocks can activate superluminal waves. Namely, they can transfer non-propagating Alphen waves into the superluminal modes. And this idea was tested very recently by Jens and Lorenzo and others with peak simulations that you can see here. So that's another possibility. It's not clear to me what's the efficiency of this process, and it's not clear to me, to be honest, but I guess Chris has an answer. How do you get these non-propagating waves at gigahertz frequencies from the cascade? But, OK, maybe an answer to this. I'll skip this. I guess I have to finish. So let me just say quickly a few words about the future. So one thing we would like to do, and it's actually something we already started to think about, is to simulate magnetized chokes, not only master, but in general magnetized chokes in a regime where the precursor wave has a large strength parameter. And the question here is how this is going to feedback on the emission mechanism. In fact, the simulation I showed earlier for the cooling, according to our estimates, they already have a strength parameter of a few. But what we actually need to do is a systematic study of this regime, and also with cooling. So this is one thing we plan to do. The other thing, which is possible with 1D simulation, we think, is to do much longer runs to capture the evolution after the shock dies. Okay, so the movie I showed you was kind of stopped before the complete dissipation of the wave. And we have some preliminary runs which suggest some interesting results, but this is something we're studying. Also, injection of more complex kilohertz waves, because until now what's been done is to inject a nice sinusoidal wave. A more complex wave may actually produce envelope on which the precursor wave can ride. I'm not sure it's true, but it's a possibility. And this can actually avoid also the large A problem. I think this is now under study in Yaji's group, I'm not sure. The other thing is this thing I mentioned is to try and study what are the observational signatures of this fragmentation in the, or maybe even more involved, configuration for propagation of a wave in a more complex field. And also a study of a multi-wavelength counterparts. So I think Michael is doing this or intend to do this in the very near future. Also, as I mentioned, what's being planned, and it's already under study, is a simulation of propagation in the regime A naught is larger than 0. And I think it's a good time to stop.